I'm going to walk through notes for trig-related rates, section 2.6. First, let's go through the steps that we're going to take for trig-related rates. First, we want to list known and unknown variables given in a problem. Right, so we want to assign values to variables that we know we're going to solve for, or variables that where we know the values and we're going to use that to help us solve our problem. Second, we're going to write the trig equation relating the variables together. Okay. And third, once we have that, we're going to differentiate with respect to time. And then finally, we're going to use trig ratios to substitute in values and then solve for the variable we're looking for. Okay, so number one, a fish is reeled in at a rate of 1 foot per second. So whenever you see the word rate or change, we know that, and also we see the this is in terms of foot per second. So we know that this has to be some sort of a rate involved. This will be assigned to a variable with some sort of a d over dt. From a point 15 feet above the water, at what rate is the angle between the line and the water changing when there's a total of 25 feet of line out? So rate of change for the angle, okay, so there's something new that I haven't seen before. This will be d theta over dt, right? Angle is theta, rate at which angle is changing, that will be a d theta over dt. Okay, let's look at the diagram here. We have a person with a fishing pole, and this distance between the fishing pole, the top of the fishing pole, and the water is not going to be changing. There's always going to be 15 feet. Now, when he casts out the line, maybe the line is out here to begin with, but as he reels in the line, this z value will decrease. Right? Can you imagine it decreasing? You can also see that the theta, the angle, is going to increase, right, as the fish gets reeled in. And also the distance, this distance x, is also going to be decreasing. So it helps to kind of visualize this problem in motion. Okay. The rate at which the fish is being reeled in, okay, so that's going to be dz dt. Okay. So that's going to be negative 1 foot per second. When there's a total of 25 feet of line out, so that's going to be z, 25 feet. We're trying to solve for d theta over dt. Okay, so let's draw a triangle, and then we can figure out the trig function that's going to relate these variables. We know that this is a distance, 15 is distance between the top of the water and the fishing pole. We know that's unchanging, so we don't have to assign a variable there. That's always going to be 15. Okay, we know this the line out is z, and then theta is what we're d theta over dt. That's what we're looking for. All right. So the variable, the trig function that we can use to relate these pieces of information together is with sine. Right. Sine of theta is equal to opposite over hypotenuse. So sine of theta is equal to 15 over z. Okay. And we can start finding our derivative. All right. But first, we can rewrite this in a form where it's easier on the right side to find a derivative. We want to do power rule. We can bring the z up to the top. So then sine of theta is equal to 15z to negative 1. Find the derivative. Sine becomes cosine. Cosine of theta. Every time we find the derivative of a variable, we have to attach a d over dt, since this is related rates, to a third variable, is equal to, go through power rule, bring down the negative 1, subtract 1 from the exponent, and then, because we just found the derivative for z, we have to attach a dz over dt. Okay. Remember our goal here, we're trying to solve for d theta dt, so I'm going to divide both sides by cosine. I'm going to clean the right side up, so negative 15 over z squared cosine of theta dz dt. Okay. Now we don't know what theta is, but we do know the ratio for theta for our, right? We know that at this moment in time, z will be 25, we know y is always 15, so this snapshot, this moment in time, we can use Pythagorean to figure out the length of x. And the length of x is simply just going to be using Pythagorean. X squared plus 15 squared equals 25 squared, so solve for x, x is 20. So cosine of theta is just going to be adjacent over hypotenuse, so 20 over 25. I can reduce this to be 4/5. So then negative 15 over z, which is 25, z squared, times 4/5 times negative 1. So again, we don't want to replace any variables with values until after we have found our derivative. Okay? We don't want to assign cosine of theta with 4/5 too early. Sorry, a sine of theta with 15 over 25 too early. We only want to assign values for variables after we've gone through the derivative process. Because if we don't, then we lose the ability to get to the variables that we're looking for, d theta dt, and also be able to use dc dt. So once we're here, we can just start clean up, start to simplify. Negative 15 over 25 squared, 25 times 25. The 4/5 can cancel out with the 5, and this comes down to be negative 3 times negative 1 divided by 5 times 20, 3 over 100, so d theta over dt is equal to 3 over 100 radians per second. Okay. Let me see if I can get through example 2 as well. Okay, a carousel has a radius of 20 feet and completes one rotation every 30 seconds. Okay, so remember, 2 pi radians is one rotation around the circle. Okay. Determine the angular velocity of the carousel in radians per second. So call this d theta dt. Okay. D theta dt is rotations per second. So we know that it will take 2 pi for one rotation, and it's going to complete one rotation every 30 seconds. So we know that if we simplify this, d theta dt will be pi over 15 radians per second, okay, which we're going to use later. Okay, if you were to ride on the carousel for 10 seconds, what angle would you be at compared when you started? So if we're traveling at pi over 15 radians per second, and if we go for 10 seconds, then if we multiply those, the seconds cancel out, and 10 over 15 pi is just 2 pi over 3 radians. We've traveled the distance of 2 pi over 3 radians. Okay, so that's going to be our theta. Okay, finally, find dx dt as a function of theta. Okay, we know that this is x. We know radius is 20. The hypotenuse is never changing. And to relate these variables along with theta, we can use cosine. Right? Cosine of theta is equal to x over 20. Okay, we're trying to get to dx dt, so we got to find the derivative. Cosine theta becomes negative sine of theta, d theta dt. X over 20 is the same thing as 1 over 20 times x. The derivative of that will just be 1 over 20. But because we're involving x's derivative, we have to attach dx dt. So to solve for dx dt, we just divide by 1 over 20 or multiply by 20. Negative 20 sine theta, d theta dt is equal to dx dt. Okay, so now, from all the information that we found from sections A through C, we can solve for d. Find dx dt when t is equal to 10 seconds. We know dx dt from part C is negative 20 sine of theta, d theta dt. Okay, so 10 seconds, we know d theta dt is going to be from part B, 2 pi over 3 radians. And we know, theta is 2 pi over 3. And d theta dt, we can pull from part A, which is pi over 15 radians. So then multiply this through. Sine of 2 pi over 3 is simply root 3 over 2 times negative 20 times pi over 15. Put all this on the same fraction, cancel out. We get negative 2 root 3 pi over 3 feet per second.